Hey guys, so non-credit test for review. Last test. I hope you guys are happy to be almost done. This test I just glancing at the review, it's very wordy in the sense that not only do you really have to make sure that you're comfortable with just the computations, but also that you're comfortable with all of the, conceptual multiple choice style questions. So, let's just get started. It's not as long as the other one. It's only 52 questions. This one won't take us as long. So, a Pew Research analysis stated that in 2012, 35.9% of the nation's young adults, millennials, were living in their parents' homes. After reading the analysis, a statistics student wanted to design a study to determine if it was higher, which of the following is an appropriate statement of the null hypothesis? Well, because our initial research, the Pew Research study, claimed 35.9%, that's what our null hypothesis is going to be. The null hypothesis is, the result based on another survey. It's your initial baseline, so to speak. So we would say that his null hypothesis is that the percentage of the millennials at his college who live in their parents' home is the same as the millennials nationwide. All right, in 2010, polls indicated that 76% of Americans favored mandatory testing of students in public schools as a way to rate the school. This year, in a poll of 1,000 Americans, 71% favor mandatory testing. Has public opinion changed? We test the hypothesis that the percentage supporting mandatory testing is less than 76% this year. Which of the following interpretations of the p-value is valid? A. So when we interpret the p-value, it's very important to kind of pay attention to what we're actually doing. When we calculate a test statistic for hypothesis testing, we assume that the population mean is the same as the null hypothesis. The null hypothesis is something that we assume to be true, and we're trying to find statistical evidence to either reject it or fail to reject it. So when we assume that the mean is the null hypothesis, that's what we're assuming to be true. So if we assume the null hypothesis is to be true, there is a 0.014 chance that the results will show 71% or fewer. A tire manufacturer has a 60,000-mile warranty for tread life. The manufacturer considers the overall tire quality to be acceptable if less than 5% are worn out at 60,000 miles. The manufacturer tests 250 tires that have been used for 60,000 miles. They find that 3.6% of them are worn out. With this data, we test the following hypothesis. The HO is that the proportion is equal to 0.05, the HA less than 0.05. When I say HO, I don't mean to, it's not bad, I mean HO, the null hypothesis HA. It's just easier to say it that way. So what assumption about the sample underlies the hypothesis test? The sample comes from a population with 60,000. Hold on, my dogs are barking. All right. So we have to assume that the sample comes from a population of tires with 60,000 miles where 5% are worn out. The sample comes from a population of tires where 250 are used for 60,000 miles. No. The sample comes from a population of 60%. No. A. We have to assume that the population does come from a population of tires, or the sample comes from a population of tires with 60,000 miles and 5% of them are worn out. Pregnancy testing. A college student has been feeling well and visits her campus health center. Based on her symptoms, the doctor suspects that she is pregnant and orders a pregnancy test. The results of this test could be considered a hypothesis test with the following hypotheses. The null hypothesis is that the student is not pregnant, and then the alternative is that the student is. Which of the following is a type 1 error? So a type 1 error is when you reject the null hypothesis, but it actually is true. So in this case, we're looking to see in which of these statements does somebody reject the null hypothesis, but it's actually true. So we would say that rejecting the null hypothesis is concluding that the student is pregnant, but the student actually is not pregnant. The student is pregnant, but the results show that so the wording is weird here. So we would say then the student is not pregnant, but the test result shows that she is, because the test is going to be us saying she's pregnant, but she really is in fact not. So the wording with that one is a little bit tricky, so just be careful of that if that's on the test. All right. The Pew Research Center reported that 36% of American millennials still live at home with their parents. A group of students wants to conduct a study to determine whether this result is true for students at their campus. They survey 300 randomly selected students at their campus and determine that 43% of them still live at home with their parents. With this data, they test the following hypotheses at the 5% level. The p-value is 0.006. So we assume that the initial research study is true, 36%. And we want to see, does that mean that there's more than that at our school? Now, in this case, we're asked to interpret the p-value, or not p-value, to kind of make a conclusion based on the p-value. So, for lack of a better word, or for lack of better words, I'm going to say to live by this guideline. If the p-value is low, reject the hoe. All right, I'll say it again. If the p-value is low, reject the hoe. That provides significant evidence that the alternative hypothesis is more credible than the null hypothesis. So if the p-value is low, reject the hoe. The natural question is, well, what does that mean? What is low considered? Usually, if it doesn't say any p-value less than 0.05, we would reject the null hypothesis. So in this case, our p-value is 0.006. So that means we have significant results. We would reject the null hypothesis and say, you know what, there's statistical evidence to support the claim that more than 36% of millennial students live at home with their parents. So the evidence suggests that more than 36% of students at their campus live at home with their parents, because 43% nope. The evidence suggests that more than 36% of students at their campus live at home with their parents because the p-value is less than the significance level. There we go. All right. In 2016, the Centers for Disease Control reported that the teen birth rate in Atlanta, or in Georgia, was 23.6%. The Atlanta City Council offers a study to see if the teen birth rate within the city is lower. So, in this study, what is considered to be the population proportion? Well, it is assumed that the null hypothesis is our population proportion. So we're assuming that it's 23.6%, and we're looking for evidence that it's actually lower. So the sample proportion is not the population proportion. A recent report estimated that 25% of all college students in the U.S. have a sexually transmitted disease. Due to the demographics of the community, the director of the campus health center believes the proportion is lower. He tests the null hypothesis, P is 0.25, less than 0.25, and the campus health center, or the 50 students, 18% have been diagnosed with an STD. Is the sample size condition for conducting a hypothesis test satisfied? So, just like before with sampling distributions, we have to make sure that both n times t and n times 1 minus t are both at least 10. So in this case, so our sample size is 50, and our null hypothesis, and we determined that, let's see, well, we're assuming that it's 0.25. So we assume that p is 0.25. We're going to do 50 times 0.25, and we only get 12.5. Okay, good. And then 50 times 0.75. I just did a weird symbol. Sorry. 37.5. So yes, because the sample is random, and then yes, also I shifted that one, because 50 times 0.25 and 50 times 0.75 are both at least 10. Question 8. In 2014, or a 2014 study by the reputable Gallup organization estimates that 44% of U.S. adults are underemployed. Underemployed means the person wants to work full-time, but is employed part-time or unemployed. We want to know if the proportion is smaller this year. We select a random sample of 100 U.S. adults this year and find that 40% are unemployed. After carrying out the hypothesis test for p equals 0.44 compared to 0.44, we obtain a p-value of 0.21. Which of the following interpretations of the p-value is correct? So remember, we're interpreting the p-value. We assume when we do these hypothesis tests that the null hypothesis value is true. We assume that the true proportion is 0.44. So we would say there is a 21% chance that 40% or fewer are underemployed this year if 44% were underemployed in 2014. That seems right. There's a 21% chance that There's a 21% chance that a sample of 100 U.S. adults will have 40. Yep. So there's a 21% chance that a sample of 100 U.S. adults will have 40% or fewer underemployed if the null hypothesis is true. Talking about the sample. Coffee. A popular chain of cafes has been receiving online complaints about one store location. Regular customers complain that the staff at this location consistently underfill their cups of coffee. The owner of the chain will personally visit the location and meet with the staff to determine if more than 10% of the 16-ounce cups were underfilled by 1 fluid ounce. She arranges to have mystery shoppers visit the store. Okay, so n is 100, a sample size of 100, and then we have our p-hat. So p-hat in this case is 18 were underfilled. So we would say 18 divided by 100. So 18% were underfilled. So we're looking to test the hypothesis that the true proportion that were underfilled is 10% versus it's greater than. So we calculate our z-score. Now, in order to do that, though, I don't want p-hat. P 0.10. We need to find a standard error. Now remember, we are assuming that the null hypothesis is true. So we are assuming that p is 0.1. So when we calculate the standard error, we use 0.1 and not 0.18. 0.1 times 1 minus 0.1 divided by 100. And then we calculate our z-score. So z is our p-hat, x minus the mean. In this case, the proportion, it's p-hat minus our assumed mean divided by the standard error. 2.6667. Now, if you're having trouble kind of determining whether or not it should be the positive or negative, if our p-hat is larger than the null hypothesis value, the z-score is going to be positive. If the p-hat is less than our null hypothesis value, it's going to be negative. And that should make sense. In our z-score calculation in the numerator, it's going to be our p-hat minus the null hypothesis. So if it's larger, it's going to be positive. All right. A quality control engineer at a potato chip company tests a bag filling machine by weighing bags of potato chips. Not every bag contains exactly the same weight. We all know what this is talking about. This happens to everyone. Sometimes you buy a bag of Lay's and there's like 2 chips in the bag. But if more than 10% of bags are overfilled, they stop production to fix the machine. They define overfilled to be more than 1 ounce. So the engineer weighs 176. We want to know the test statistics. So it's basically this question again. So I'm going to alter my formula from the previous question a little bit just so we can click. 1 minus this. Hello. Divided by n. There we go. All right. So now what we can do is just change our values. I have everything in here. So we have 176 bags. Our p-hat is 42%. So we do 40, or not 42%, but 42 out of the 176. That's our p-hat. Our null hypothesis is once again 0.1, and it calculates everything for us. So z is, how many decimals? 2. 6.13. Let me just double check to make sure that's right. Our n is 176. P-hat is 42 out of 176. Our null hypothesis value is 0.1. We do, just an error, B3, 1 minus B3 over B1. There we go. Okay, good. 6.13. Does secondhand smoke increase the risk of low weight birth? A baby is low birth weight if it weighs less than 5.5 pounds at birth. According to the National Center of Health Statistics, about 78% of all babies born in the U.S. are categorized as low birth weight. Researchers randomly select 1,200 babies whose mothers had extensive exposure. 10.4% of the sample is categorized as low birth weight. Which of the following are the appropriate alternative in null hypothesis? So, we want to know, does secondhand smoke increase the risk? So we want increase. We want a higher percentage. Oh, let me save it for question 11. All right, we want to know, so our null hypothesis is this value of 7.8%. So we're looking for which options have the null hypothesis as 0.078. And we want to know, in a group of smokers, does that increase, does the rate at which you have your low birth weight, does that increase? So our null hypothesis is 0.078. Our HA is greater than 0.078. Okay? So taking a class in a short-term format, 8 weeks, instead of 16 weeks, increase a student's likelihood of passing the course. For a particular course, the pass rate for the 16-week format is 59%. Yikes. A team of faculty examined student data from 40 randomly selected accelerated classes and determined that the pass rate is 78%. So we're looking at, our null hypothesis is 59%. And we're looking for greater than 0.59. Yeah. Which of the following situations involves testing a claim about a single population proportion? A recent study estimated that 20% of all college students in the U.S. smoke. The head of the Health Services at Goodhart University suspects the proportion of smokers may be lower there. That's true. B is about means. C is about, it's a two-sample one. Yeah, this is a single population proportion, A. That's what we've been working on. Okay. According to the Pew Research Center study, in May 2011, 39% of all American adults had a smartphone, one which the user can use to read email and surf the internet. A communications professor, higher, okay, we have she selects 286 community college students and finds that 133 have a smartphone. So let's just alter, we have everything typed in before, so we're just going to do the same thing. N is 286. Our p-hat then is 133 out of 286. Our null hypothesis now is 0.39. And then everything should now be the same. Once you have your values typed in, like I said, I think I do this in every video, you really want to try and do something like this if you don't think you can remember the formulas and do them over and over again. Doing these types of calculations in Excel and just leaving these values here will greatly reduce the amount of time that you're spending taking the test. So 2 decimal places, 2.60. According to, okay, well this one actually does everything for us already. It's the same question, but now we're given the test statistic, and now we have to interpret or find the p-value. So let's just do that, p-value. So the calculation of the p-value is really important, and it's kind of tricky if you're not paying attention to the problem. The method that you use, or the syntax that you're going to type into Excel, is going to be determined by the alternative hypothesis, greater than in this case. So if think back to I think that was the second test, to be honest. When you wanted to find greater than probabilities involving the normal distribution, you have to do that 1 minus. So we're looking for the probability that our test statistic is greater than 2.3779, and we do greater than based on the alternative hypothesis. So we do 1 minus norm S diff because we're dealing with a standardized value, and we're going to do 2.3779, and if you recall, the cumulative is always 1. And there's our answer, 4 decimal places, 0.0087. And if you want, I mean, I can show you that the calculations involved in calculating the test statistic will give you the 2.3779. Our n is 339. Our p-hat then is 136 out of 339. And our null hypothesis is 0.34. And if you look, there's our 2.3779 and in our p-value calculation. All right, moving on to means. A medical researcher is investigating the effect of drinking coffee on systolic blood pressure. The researcher assumes the average systolic blood pressure is 120. Well, because we're assuming that's true, that's going to be our null hypothesis. Maybe. That might be the trick question, though. So for a random sample of 200 patients, the researcher takes 2 measurements. The first systolic blood pressure measurement is taken during a week when the patient drinks no coffee. And the second systolic blood pressure measurement is taken during a week when the patient drinks at least 2 cups of coffee. The medical researcher wonders whether there is a significant difference, keyword here is difference, between the blood pressure measurements. So, this actually changes the answer a little bit. Because we're taking 2 measurements from the same person, we want to know, we assume that there is no difference. That's what the null hypothesis mu is 0 means. There is no difference in systolic blood pressure between drinking coffee and drinking coffee. And we're testing the hypothesis that drinking coffee actually makes that difference not 0. Not 0 means there is a difference. One of the 2 is higher. Okay. According to a 2014 research study of national student engagement in the U.S., the average college student spends 17 hours per week studying. A professor believes that students at her college study less than 17 hours per week. 80 students, okay? From her survey data, the professor calculates the mean number of hours per week spent studying. For her sample is 15.6 and a standard deviation of 4.5. The professor chooses a significance level of 5%. What can she conclude? Well, the professor cannot conclude why, okay, nothing, the conditions for using a T model are not met. Well, our sample size is 80, so, we can trust that we can do that, assuming that there's no major skewness. So let's just see. Our null hypothesis is 17. Just look at our X bar and our standard deviation. So, I'm going to say B. The professor cannot conclude that the average number of hours spent per week studying is less than 17 hours per week. The sample size, or the sample mean of 15.6 is not significantly less than 17. And you should kind of see that just from your X bar and your standard deviation. Remember the standard deviation is your typical distance from the mean. So that means, think about your normal distribution. 68% of your data is within 1 standard deviation, 95% is within 2. So 17 is definitely going to fall within that range. Okay. According to Facebook's self-reported statistics, the average Facebook user is connected to 80 community pages, groups, and events. For a statistics project, a student at CCC tests the hypothesis that CCC students will average less than 80. She posts a survey on her Facebook page. Well, she cannot use the t-test for this, because it's not a random sample. It's a voluntary response sample. All right. An urban planner is researching commute times in the San Francisco Bay Area to find out if commute times have increased. In which of the following situations could the urban planner use a hypothesis test? All right. The urban planner has a random sample of 110 commuters. Who believe their commute time has increased. Doesn't seem very good to me. The urban planner collects travel times from a random sample of 125 commuters in the San Francisco Bay Area. A traffic study last year claimed that the average commute time is 45 minutes. The urban planner will see if there is evidence that average time is greater than 45. Okay. The urban planner asks a random sample of 100 commuters in the San Francisco Bay Area to record travel times on a Tuesday morning. 1 year later, the urban planner asks the same 100 commuters to record travel times on a Tuesday morning. The urban planner will see if the difference in commute time shows an increase. I'm going to say that's the best one. I'm reading though. Yeah, I'm going to say that one. Alright. We have the null hypothesis is that the mean number of insect parts per 100 is 75. The alternative is that it's greater than 75. Is the following a type 1 error or a type 2 error? The test fails to show that the mean number of insect parts is greater than 75 when it actually is. So in that case, what we've just done, we failed to show that it's greater. That means we failed to reject the null hypothesis. That means type 2 error. So a type 1 error is when we reject the null when it's actually true. A type 2 error is when we fail to reject the null hypothesis when it's actually false. Okay. CHDS has been collecting data about expectant mothers in Oakland, California since 1959. One of the measurements taken by CHDS is the weight increase for expectant mothers in the second trimester. In a fictitious study, suppose that CHDS finds the average weight increase in the second trimester is 14 pounds. Suppose that in 2015, a random sample of 40 expectant mothers has meaning. Yeah, okay. All right, what is the most appropriate conclusion? So we're interpreting the p-value. So there is a 2.1% chance that a random sample of 40 expectant mothers will have a mean weight increase of 16 pounds or greater if the mean second trimester weight gain for all expectant mothers is 14 pounds. That seems pretty good to me. No, B is not right, C is not right. I'm going to read D. There is a 2.1% chance that the population of expectant will have a mean weight increase of 16 pounds. It's the mean, let's see. I think it's A. Read. Okay. A criminal investigator conducts a study on the accuracy of fingerprint matching and recruits a random sample of 35 people to participate. Since this is a random sample of people, we don't expect the fingerprints to match the comparison prints. In a general population, a score of 80 indicates no match. Scores greater than 80 indicate a match. If the mean score suggests a match, then the fingerprint matching criteria are not accurate. The null hypothesis is that the mean score is 80, and the alternative is greater than 80. The criminal investigator chooses a 5% level of significance. She performs an experiment and analyzes the result. The result chooses a t-test for mean and obtains a p-value of 0.04. So, 0.04, remember from before, if the p-value is low, reject the hoe, lower than the significance level. So, in this case, 0.04 is less than 0.05, so we would reject the null hypothesis and say that the mean is greater than 80. There is statistically significant evidence to support the claim that the mean match score is greater than 80. What is the sample size? 35, that's fine. Just proves there is evidence. Nope. Yeah, because we have 35 people. We need at least 30. So the sample size criteria seems to be met. But, yeah, I'm going to stick with A. This proves, though, that's the tricky part. I don't like the word disproves. I don't like the word disproves, though. It doesn't prove anything. It just provides evidence. So, all right. I'm going to stick and say disproves there is evidence because the sample size is large enough, and I just don't like the word that disproves. I'm going to save it just in case. What question are we on? Alright. So yes, I'm just going to say, the p-value is low, so we're going to have to reject the null hypothesis, and our sample size criteria is matched. It's just this wording to me. It just doesn't... Alright. Let's do this. P-value calculations. A group of 53 college students from liberal arts college were randomly sampled. So N is 53. The purpose of this study was to compare the drinking habits of the students at the college to the drinking habits of college students in general. In particular, the dean of students who initiated this study would like to check whether the mean number of alcoholic drinks that students at his college in a typical week differs from the mean of U.S., which is estimated to be. So our null hypothesis mean is 4.73. X bar. A group of 53 students reported an average of 4.9 and a standard deviation of 3.74. So we need to calculate the standard error. And we calculate that as S divided by the square root of N. And then we calculate our z-score. Actually, it's not a t-score, it's a t-score, because we're using, it's t because we're not given the population standard deviation. So t is equal to x bar minus the null hypothesis divided by the standard error. Now, all we need left is the degrees of freedom. The degrees of freedom is n minus 1. And then a p-value. So, p-value. We are looking to see, in particular, the dean of students who initially would like to check whether the mean number of alcoholic drinks differs from the mean. So we're not looking for any particular direction. So if you look in t-distribution, t-dist, there are three options: t-dist, t-dist.qt, and t-dist.rt. Those three are going to be your three directions. So t-dist gives you a left tail direction. That means your null hypothesis is less than. t-dist.qt is when you have no direction, you're looking for just not equal to. And .rt is a right tail. So this is a two-tailed test. Our t-score is 0.3309, and then our degrees of freedom is 52. Our p-value is 0.7420. This seems really big. Well, our standard deviation is pretty... Let me see. I'm going to go back really quick. I don't know why. I have this. Here we go. Go back to 17. I want to see the standard error of this question. I just used S, but let me just see. 4.5 divided by the square root of... Where's our n? 80. 0.5. So then we would do a z-score. Let's do 15, or t-score, 15.6 minus 17 divided by a standard error. Negative 2.78. just stop. Degrees of freedom is 79.1. Ooh. It supports it. Because our standard error actually of the sampling distribution, I didn't calculate that, I just thought of it now, is 0.5. So actually the answer to 17 should be A. Going back to the test. Okay. 24. Commute times in the U.S. are heavily skewed to the right. We select a random sample of 60 people from the 2000 U.S. Census who reported a non-zero commute time. In this sample, the mean commute time is 28.5 minutes with a standard deviation of 18.8. Can we conclude from this data that the mean commute time is less than half an hour? Okay, so I have everything typed in, so we're just going to use this. Our sample size is 60. We are less than half hour, so we're going to set up a null hypothesis of that it's equal to 30 minutes. So that's going to be our null hypothesis value. Our x bar is 28.5. Our standard deviation is 18.8. And then assuming we type everything in, everything else should be good now, except our p-value. So let's just look at this. We want to less than half hour. So t.dis is going to be our function here. T.dis because we're looking at less than 30 minutes. So t.dis, this degrees of freedom, and then our cumulative is 1. So our p-value is 0.2695. And remember, if you don't like rounding, just use Excel, and you can always, use those decimal rounding buttons. Okay. Dean Halverson recently read that full-time college students study 20 hours each week. She decides to do a study at her university to see if there is evidence that students study an average of less than 20 hours a week. A random sample of 30, so n is 30. Our null hypothesis is 20. No. Yeah, less than 20. So our null hypothesis is 20. And we found that the average number of hours of the 30 students studied each week was 18.7. That's x bar. And then our standard deviation is 3.4. That might be it. Let's see. We want less than. We're going to say about 37, less than, yeah. And that's t-dis already, so we can just find the p-value of 0.0225. So remember, when we calculated our p-value here, we used just t.dis because our alternative hypothesis is less than 20 hours. Okay. A medical researcher is studying the effects of a drug on blood pressure. Subjects in the study had their blood pressure taken at the beginning of the study. After being on the medication for 4 weeks, their blood pressure is taken again. A change in blood pressure is recorded and used in doing the hypothesis test. Change is final minus initial. The researcher wants to know if there is evidence that the drug pressure, or the drug affects blood pressure. At the end of 4 weeks, 34, so n is 34, 34 subjects had its average change in blood pressure of 2.5, so that's our average, 2.5, with a standard deviation of 5.1. The question here is, what's the null hypothesis? Well, think back to that question before. We're taking the difference. So we assume that there is no difference in final and initial. Well, if there is no difference in final and initial, what would the difference be? We're assuming they're the same. If they're the same, we take their difference, the difference is 0. And so then, we want just no difference. So, it doesn't say if it lowers or if it raises it. Let's see. It just says the researcher wants to know if there is evidence that the drug affects blood pressure. So it doesn't specify if it lowers or raises it. So we're going to do a two-tailed test and just say what's the probability that it's different. 0.2143. All right. So I realized that my degrees of freedom was off. That's not 0.2143. It's 0.0073. But I have to now check and make sure that, I hope these are all right. I'm sorry, I realized I had 1 degree of freedom with my cumulative. Oh, that's why. Never mind. Let me just check. Question 25. Let's see. N is 30. The null hypothesis is 18.7. No. 20. 18.7. S is 3.4. Yeah, okay, yeah. And this is a left-tailed test. Oh, 25, that's right. And is 60. The null hypothesis is 30 minutes. X bar is 28.5. S is 18.8. So 2695. Okay. N is 53. Ho is 4.73. X bar is 4.90. S is 3.74. And we want in our test, differs. So T is dot 2T. Okay. Just that one. So with number 26, I had 0.21 something, but just know that it was supposed to be a little different because my degrees of freedom were off in my calculations. I had a comma 1 right in here. So just be careful. The answer is 0.0073. Let me save it real quick. Alright. What question are we on? 27. Okay. Let me just clear all this. Find the p-value for the hypothesis test. A random sample of size 54 is taken. The sample mean... okay. A random sample of size 54 is taken. So n is 54. The null hypothesis is 400. X bar is 426. S is 82. So the standard error and the t-score are automatically calculated for us. So it's really just a p-value that we have to check for. So in this case, we're looking for greater than. So that's going to be a two-tailed test, or a right-tailed test. So t disrupt RT, t-value, the degrees of freedom. What did I type wrong? B15, B16, that's right. So 0.0118. Number 28. Find the p-value for the test. A random sample of size 51 is taken. The sample has a mean of 423 and a standard deviation of 84. Everything else is the same. So now the p-value is different. So in this case, our alternative hypothesis is not equal to. So this is a two-tailed test. T is 1.955, and then the degrees of freedom is 50. Why do I give me the error? B15 is our T, B16 here. 0.0561. Last one with this type of question. Sample size, mu is still 400. Sample size is 52. X bar is 388. S is 85. And we want a T dot diff. T dot diff because the alternative hypothesis of 29 is less than. So T, comma, degrees of freedom. Oh, and then comma 1. 0.1567. Number 30. Child health and developmental studies have been collecting data about expectant mothers in Oakland, California. One of the measurements taken by CHSD is the weight increase, okay? In a fictitious study, suppose that CHSD finds that the average weight increase is 14. Okay, let's do our null hypothesis is 14. A random sample of 34 expectant mothers, a mean weight increase of 15.9, with a standard deviation of 6.2. So, standard error is S over root n. T is calculated the same way as before. The degrees of freedom is 1 minus the sample size. It's just the p-value that we need to calculate. So we want a hypothesis test is done to see if there is evidence that the mean weight increase is greater than 14. So we use pdist.rt, the right tail test, with t, comma, the degrees of freedom, 0.0416. All right. In a study at West Virginia University Hospital, the questionnaire filled out, in the study, the researchers sent a 22-item survey to 1,000 cancer patients. They collected demographic, okay? The questionnaire filled out by cancer patients at the West Virginia Hospital also asked if they were current smokers. The current smoker rate for female cancer patients was 11.6. 95% responded for male, 10.4. Can we use a normal model? So we have to check 4 different things. N times P for both groups. So we're going to do it for the females first. So we're going to do 95 times, for females first, 0.116. Oops. There we go. 11.02. Then we're going to do N times 1 minus P. 95 times 1 minus 0.116. So for the female groups, it's good. Let's just check the males. 67 times 0.104. Nope. So, a normal model is not good, because for the males, it's not at least 10. Alright, the histogram below is a simulation of the difference between 2 population proportions. The mean and the standard error are calculated using the population proportion values in this. Okay? Which of the following is the best estimate of the population proportions? Well, just look at the mean. The mean looks to be about negative 0.15. So let's just look and see which of these have a difference of 0.15. A is 0.05, B is 0.2, C is 0.1, and D is negative 0.15. That's all you have to look at. We're looking for the mean of the distribution, which is negative 0.15. So which of these has a difference of really negative 0.15? The histogram below is a simulation, same thing. Which of the following is the best estimate of the standard error? Well, our mean is once again negative 0.15, and it says that, well, first of all, standard error can never be negative. So please know it's not A or C. 0.15 away goes all the way over to 0. That's not going to be true. That's too far. So the standard error is 0.05. It's the standard deviation of the distribution. So if you look, it looks to be about, if you go to the right and left, to negative 0.1 and negative 0.2, that's about a distance of 0.05. Alright. A popular Skittles candy comes in 5 colors. According to the Skittles website, the colors are evenly distributed in the population of Skittles candy, so about 20%. So they buy 2 small bags of Skittles. We determine the percentage of green Skittles in one bag and the percentage of orange in the other. Suppose that each bag contains 40 candies. Which of the following give a sample difference of 0.1? Alright, so let's just say we have 10 green, do 10 divided by 40. That's the proportion of green in the first bag, minus 6 out of 40, the proportion of orange, 0.1. Oh, there you go. And you can even see, let's just do the other ones. That would be 4 out of 40 minus 8 out of 40, negative 0.1. And then we do 10 out of 40 minus 10 out of 40, which is 0. So, alright, every simulation in this module is based on the assumption about the difference, blah, blah, blah. The distribution of differences between the sample proportions shown below has a mean of 0.35 and a standard error of about 0.1. Which of the following did we use to generate this sampling distribution? Well, we want to look and see, first of all, which of these differences is 0.35? 0.85 and 0.65 is 0.2. And I'm saying 0.35 because that's the mean of the distribution. We're taking the difference of two values and calculating the sample distribution. So that means the answer is B or C. So all we need to do then is if we know the population proportions and we know the sample size, which we're given here is 35 or 20, let's just see which of these gives a standard deviation or a standard error of 0.1. So we're going to have to calculate two standard errors. We haven't done this yet in the video, but when you have the sampling distribution for the difference of two proportions, the calculation for the standard error is a little different. It's p hat 1 times p hat 2 divided by n1, or p hat 1 minus p hat 1 over n1, plus p hat 2 times 1 minus p hat 2 over n2. It's basically the same calculation we did before, but we got to do it twice. So if we're looking at answer choice B, let's just see if this is the answer. We assume that the proportions are 85 and 50, so we're going to do 0.85 times 1 minus 0.85. And then it says sample size is 35. So let's just do divided by 35. So the first part of the standard error is p hat 1 times 1 minus p hat 1 over n plus, let's do now the same thing with 0.5. 0.5 times 1 minus 0.5 divided by 35. And we just want to see, does this give us our standard error of 0.1? Okay. Which does. So the answer is B. And you can note, if you did size 20, all we're going to change is the denominator here, 0.2, or 20, not 0.2, instead of 35, 20, and that would mean our standard error is 0.14. 36. All right. In a study, yep. Okay. N is 1419. We've done a survey of 1,419 patients. P hat -- 284 patients responded for various reasons. Researchers only used 255 of the completed surveys. Okay. So we're going to do N1, P hat 1, N2, P hat 2. So N1 is female. So N1 is 143. And that means that P hat, of those people who responded who were cancer patients who were female, that's 38 out of 143. And then N2 is 112. And then our P hat for the males is then 62 out of 112. Calculate the difference between the corresponding sample proportions. So that's it. Okay. So the difference is P hat 1 minus P hat 2. Wait, let's see. We want female minus male. Yes. So it'll be P hat 1 minus P hat 2. 3 decimal places. So negative 0.288. All right. In 2014, yep, standard error formula, that's your P1 minus times 1 minus P1 over N1. That's that formula for the standard error and the difference of proportions. Calculate the standard error. So we know it's going to be the square root, gives you everything you need. P1 is 0.33, 1 minus 0.33, divided by N1, plus 0.25 times 1 minus 0.25 over 97. 0.33 times 1 minus 0.33 over 121 plus 0.25, yep. How many decimals? 3. 0.061. Oh, wow, what did I do? All right, 38. And then, okay, so the difference is 0.05. That's the center of the distribution. I'm skipping a lot of the words. But it wants to know, from this distribution, consider simulating this data with 5,000 samples. Based on the sampling distribution of difference in proportions, which is above, which of the following results for P1 minus P2 will be most unusual? So what we're looking for is which one's furthest away from the mean of 0.05. So 0 is pretty close. Negative 0.06 is pretty close. Negative 0.1 is 0.15 away, but 0.29 is really far away. 0.29 is furthest away right here. That's 0.24 away. So we're just looking for here, which would be most unusual, the one that's furthest away from the mean. Okay. In the article, Coffee, Caffeine, and Risk of Depression Among Women, September 2011, okay, the participants in the study were older with substantially lower rates of depression when compared to female teens. Researchers compared two groups of women, those who do not drink coffee and those who routinely drink 4 or more cups of coffee each day. For the following question, a coffee drinker is a woman who drinks 4 or more cups each day. Suppose that the difference between the proportions of coffee drinkers and non-coffee drinkers is negative. So the statistic is P hat for coffee drinkers minus for non-coffee. So, in this question then, it tells us that so we have coffee minus non-coffee. We calculate that point estimate, and it says that this is less than 0. And we know that because it's negative 0.02. So that means that the rates for coffee are less than the rates for non-coffee. Which means who has a higher of your non-coffee drinkers. Non-coffee drinkers have to be higher for that difference to be negative. All right. We have a sampling distribution. The difference in proportions is 0.05. And a standard error is 0.08. And the z-score is 0.885. Okay. So it gives us a z-score. Let me just read again. Let me just see. In 2014, students in an advanced stat class at UC Berkeley conducted an anonymous survey about use of cognition-enhancing drugs among college males. One survey group of males included members of a frat, and the other included no frat. We can use a simulation model to estimate the difference between the proportion of fraternity members. All right, sampling distribution. So let's just look. Where is 0.885? Let's see, 0.05. I just want to see, is there a difference? I didn't read it all the way. Oh, let me save. Alright, so let's just save it really quick. If that came up. Alright. So going back to this question, but if you see the z-score is 0.885. So I'm going to go ahead and say that even if you look at this distribution, 0 is really close to the mean. So a difference of 0, or a z-score of 0.885 is pretty close to 0. It's not greater than 2 or less than negative 2. So I'm going to say that there is not a statistically significant difference between the proportion of frat members who've used them and the proportion who do not use them. All right. So the following question, one of the graphs below represents a sampling distribution of differences between these sample proportions of coffee. Under the assumption that both women who drink coffee and do not drink coffee have a 6% depression rate, which distribution is centered correctly? Well, if you're assuming that both groups have a proportion of 6.06, that means that your sampling distribution is going to be centered at 0 because you're looking at the difference. So if you're assuming that they have the same proportion, the difference is the 0. So A 42. According to a report on the academic cheating by ETS, the Educational Testing Service, college students majoring in business and engineering are more likely to cheat than students in other majors. For a statistics project, a community college student at DVC decides to investigate cheating on 2 popular majors, business and nursing. She convinces professors who teach business and nursing to distribute a short anonymous survey to their classes. The question about cheating is one of the many other questions of college life. For this data, the student plans to calculate a confidence interval for the difference in 2 population proportions. Which is the most reasonable description of the 2 populations? Well, business and nursing. Business and nursing in the classes that were surveyed. Business and nursing here at DVC. Business and nursing at the community college. At community colleges, no. No. So it's going to basically be nursing courses. Yeah. All right. We have a confidence interval question about margin of error. We also calculate a 90% confidence interval. How does a 90% confidence interval compare to a 99%? Well, a 90% confidence interval, the margin of error will decrease. And if you think about that, remember the z-scores. The z-score for a 90% confidence interval is 1.645. The z-score for 99% is 2.5758. So the margin of error is going to have a greater multiplier for 99% versus 90%. So the margin of error decreases. This is false. Let me tell you why. So we need to check n times p and n times 1 minus p for both groups of people, meaning the number of successes in each group and the number of failures in each group is at least 10. Well, if we calculate 42 out of 50, that means n is 50, our p hat is 42 out of 50. That's met. But if you calculate n times 1 minus p for this group, that's going to tell us our sample size is 50 times 1 minus 42 out of 50. We're going to get 8, not 10, so false. All right. In March 2015, the Public Policy Institute of California, PPIC, surveyed 7,525 likely voters living in California. In the survey, respondents were asked about global warming. PPIC researchers are interested in the difference in viewpoints across racial or ethnic groups. PPIC results show that 75% of Latinos view global warming as a serious problem, and 46% of whites view global warming as a serious problem. Using the data from the survey, we calculate the sample differences in global warming viewpoints for Latino respondents and white respondents. Researchers can use the 29% sample difference to draw conclusions about what population Latinos and whites living in California who are likely to vote, because that's what our survey was. That's from where our survey was taken from. 7,525 likely voters in California, and then we sampled Latinos and whites. All right. We have a confidence interval, and that confidence interval is negative 0.1036 to 0.0882. So what is a valid conclusion? We are 99% confident that the proportion of smokers who will quit smoking with a nicotine patch is about 8.8 to 10.4% higher. No. Well, here's what we're doing. We're assuming we take the difference in proportions. And what number lies inside that interval? 0. So because 0 is a plausible value for the difference in proportion of smokers who quit, that means that there really isn't evidence that the nicotine patch is effective. and it's because 0 lies in the interval. 4T7. Okay, the New England Journal of Medicine published the results of a double-blind, placebo-controlled experiment to study the effect of nicotine patches and the antidepressant bupropion. Okay, with the data from the experiment, we calculated the sample difference in the quit smoking rates for the nicotine group and the placebo. We did treatment minus placebo. We get 0.8%, which is the following is a perfect conclusion. In this experiment, the nicotine treatment had a higher success rate than the placebo, but the improvement was less than 0.1%, or less than 1%. That is true. Because the difference, treatment minus placebo, is 0.008, they had a higher success rate, but that improvement was only less than 1%. And then based on this, though, we don't know anything else, so we don't know anything about being statistically significant. Yeah. Confidence interval, almost done. Alright. So, the difference between teenage female and male depression rates estimated from two samples is 0.07. The estimated standard error of the sampling distribution is 0.03. What's the 95% confidence interval? Well, this is easy. We take our point estimate, which is the difference, 0.07. We subtract our z-score times the margin of error. 2 decimal places. 0.01. And we do the same thing, but we just add instead. We do 0.07 plus 1.96 times 0.03. 0.13. All right. Previous studies suggest that the use of nicotine replacement therapies can help stop smoking. In this experiment, so we have N1, P hat 1, N2, P hat 2, standard error. So N1, taking a placebo, so we want 176 taking a placebo, 22 stop smoking. N2, 275. P hat 2, 81 out of 275. So the standard error is the square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 over N2. 3 decimal places. 0.037. Question 50. Confidence interval. Okay, so we have the same kind of idea as before. In this experiment, researchers randomly assigned smokers to treatment. So, we want to do treatment effect. Alright, so we're going to do treatment as N1. Alright, so N1 is 272. And then we have 82 out of 272. N2 is 162. And then we have 28 out of 162. And then because we calculated this all before, everything's already calculated for us. Calculate the 99% confidence interval. Alright, so that means we now need a point estimate. So it's going to be P hat 1 minus P hat 2. And then we need now our margin of error, which is our z-score of, actually let's just do this. Z-score, 2.576. So our margin of error is our z-score times the standard error. And now we need a lower and an upper. So we take our point estimate, subtract the margin of error, and our point estimate plus the margin of error. Let me double check that. Yeah. So, round your answer to 3 decimal places. Put, actually make the effective appropriate on. Yes. Okay. All right. So, let's just look. Oh, look, it even gave us a standard error. The only reason why I'm hesitating is I'm not sure. It just says the treatment effect. So, there are two choices here that we could do. Because it says treatment effect, I'm going to look at instead calculating p hat to placebo minus treatment. And see what that gives us. Because treatment effect, we're just kind of looking at that one being the second one, seeing if it makes it negative. So treatment effect, point estimate is going to be our placebo minus treatment, and then everything else is now the same. So we want three decimal places, so negative 0.233 to negative 0.024. All right. 2 questions left. Gardeners on the West Coast. Actually, let me just go back to this question though. We'll just see if I get it wrong with this one. But if they want the positive, it depends on what they want for the point estimate. I really think it's going to be the placebo minus the treatment. But if you did the point estimate the other way around, it's actually not technically wrong. It just depends. We should probably specify which difference to look at. I'll probably add that into the question. Yeah, I'll add that into the question before any test happens, just so we can make sure. I'm going to stick to say placebo minus treatment to keep it negative. Anyways, margin of error. The standard error, and it even gives you everything you need. In this case, the margin of error is just your z-score times your standard error, 0.09. 3 decimal places. Let's save real quick. .232. Okay, last question. The 99% confidence interval with the difference of proportions of women and men who support stricter gun control is 0.02 to 0.08. Difference here is women minus men. Which of the following conclusions about the confidence interval is most appropriate? Well, how do we interpret a confidence interval? We are 99% confident the difference between the proportions of women and men who support stricter gun control is between 0.02 and 0.08. Just because we're using 2 samples doesn't change the fact, it doesn't change the interpretation. We don't talk about any confidence intervals giving us a 99% chance, and then that's not right either. So, let's see, how did we do? $99%. I mean, I got one question wrong. What is that? Did I skip a question? Oh, I knew it was going to be this question. Wait, what? Incorrect. You are correct that the variable difference in commute time for each person is quantitative. This is a matched pair situation, so the urban planner can use a hypothesis test for a single mean. However, there is at least one more choice in which the urban planner can use. Oh wait, was this check? Oh man, I didn't read check all that apply. Man, I'm so sorry. The answer number 19, check all that apply. I'm kind of happy I make these little stupid mistakes. This is the only question I got wrong, because I hope for you guys watching it that you guys can see, oh, there are certain situations where you have to be careful and read. So this one's a check all that apply. So part C was correct. But if we look at these problems, we can also check 45 minutes. If there's an evidence of an ad. We can do B as well. If they believe. Yeah, it's going to be B and C. I didn't check B. I'm so sorry. This one is just because the people were just asking, do you think your commute time is bigger? I'm going to say it's B and C. Yeah, especially when A talks about proportions. We don't want that. We want population mean. So anyways, question 19, B and C, but everything else is right. This is the first time I've gotten most of the questions correct. So anyways, I hope this helped. As always,